Hi, welcome to Discovery of the Top Quark. The discovery of the top quark was announced in 1995 by CDF and D0, which were both experiments at the Tevatron at Fermilab. The Tevatron accelerated protons and antiprotons up to energies of almost 1 TeV. These protons and antiprotons were then collided inside the CDF and D0 particle detectors. The Tevatron, and therefore the CDF and D0 experiments, ran from the mid-1980s to 2011. You might recognize the name CDF, as that's the experiment which put out a new measurement of the W boson mass last year that appears to disagree with the predictions of the Standard Model. These experiments have a long history. If you want to know more about that aspect of particle physics experiments, you might want to check out the video Human Timescales in Particle Physics, available on this channel. Here are the references for the CDF and D0 top discovery papers. You can also find these in the description below. This video will refer to some statistical concepts that we won't explain here, but are explained in other videos. We'll be referencing the 5 sigma convention that particle physics experiments often use for deciding whether or not to declare discovery. If you want to know more about that, you can check out the videos in the playlist entitled Understanding 5 Sigma. We will also briefly mention Poisson statistics, which you can learn about in the videos in the Poisson statistics playlist. And finally, we will mention p-values, which are a measure of how well or poorly an experimental result agrees with expectation. To learn about that, you can check out the video What's a p-value? Okay, so first we'd better do an extremely quick review of some points of the Standard Model of particle physics. In the Standard Model, we have 6 quarks and 6 leptons and their antiparticles. The quarks each come in 3 colors. The quarks come in 6 types: up, down, charm, strange, top, and bottom. There are 3 charged leptons: the electron, the muon, and the tau. Each also comes with an associated neutrino. The quarks and leptons interact through the electromagnetic and weak and strong forces. These forces are mediated by the gauge bosons. The photon mediates the electromagnetic force, the Z and W bosons mediate the weak force, and the gluons mediate the strong force. Lastly, we have the Higgs boson. The topic of this video is the top quark. Okay, as we said, the electromagnetic, strong, and weak forces are mediated by the gauge bosons. Let's look at how the top quark interacts with those gauge bosons. First, let's look at how the top quark behaves under the electromagnetic interaction. A top quark can absorb or emit a photon, denoted here as gamma. Similar diagrams also hold for all of the charged quarks and leptons, so the up, down, charm, strange, and bottom quarks, and the electron, muon, and tau. All the quarks and leptons except the neutrinos. Okay, next, the strong force. The top can similarly absorb or emit a gluon. In doing so, the color of the top quark changes. Similar diagrams hold for the other quarks, but not for the leptons. This interaction will be very important for top production, as we'll see shortly. Okay, and now for the weak gauge bosons. First, the top can emit or absorb a Z boson, similarly to the diagrams we've already seen. There are also similar interactions between the Z and the other quarks and leptons. Now, In order to talk about how the top interacts with the W, we have to look back at the standard model particle content. You might notice that we've arranged the quarks and leptons each into 3 pairs. Here, we'll write that a bit more explicitly. These families are related to how the quarks and leptons interact with the W, and we'll see how this relates to the top quark in a minute. I will tack on a detail here for the physics students. I'm ignoring mass mixing in the quark and lepton sectors. We don't really need to think about that for this video. Okay, so the W mediates an interaction between the family that includes the top and bottom quarks. This means we can write down a diagram that represents, for example, a top quark emitting a W+ and turning into a B quark. There are also similar diagrams for the other families of quarks and leptons. This will be very important to understand how a top quark decays. Okay, with that, let's look at how top quarks were produced at the Tevatron and how they subsequently decayed. The CDF and D0 experiments collided protons with antiprotons at a center of mass energy of 1.8 TeV. Now, protons are not fundamental particles. They are made of constituents. So, for example, we can consider an up quark in the proton and an up anti-quark in the antiproton. Earlier, we mentioned how a top quark interacts with a gluon. And we said that similar diagrams exist also for the other quarks. Let's take that diagram that we drew before for a top interacting with a gluon and turn it on its side. Here we should note that we're using the convention that arrows are reversed on antiparticle lines. Then, if we read this diagram as time flowing from left to right, this represents a gluon disintegrating into a top-antitop pair. Now, let's attach an up-type quark-antiquark pair to the front. This new diagram represents an up quark and antiquark colliding and producing a top-antitop pair through an intermediate gluon. We can also put other quark-antiquark pairs in the initial state, not just up-type ones. Okay, so back to the Tevatron. An example process is that an up quark in the proton and an up antiquark in the antiproton can collide and produce a gluon. This gluon can then disintegrate into a top-antitop pair. Similarly, this same process can also happen with other quark-antiquark pairs in the initial proton and antiproton. Now, the process of quarks colliding and producing a gluon, which then goes to a TT-bar pair, is not the only way that top-antitop pairs are produced at the Tevatron, but it is the main way. Fun fact, because the Tevatron collided protons and antiprotons, but the LHC collides protons with protons, this is not the main production diagram for top-antitop pairs at the LHC. Okay, so we saw how top-antitop pairs are produced. After they're produced, they decay. Let's look back at that interaction between a top, a bottom quark, and a W that we said would be important for top decay. This diagram can represent a top quark emitting a positively charged W and turning into a bottom quark. The W+ is unstable though, and then decays to a fermion and an antifermion. This can be a quark-antiquark pair, like a charm quark and a strange antiquark, or a positively charged lepton and its associated neutrino. In these diagrams, I've shown how a top quark decays. For a top anti-quark, we change all particles in the diagram to their antiparticles. Okay, so let's look back again at the top-antitop pair that has been produced in a collision. On the right side, we have a top quark, which decays to a bottom quark and a W+. The W+ then decays. It can go to an up or charm quark, which I've denoted QU, and a down or strange antiquark, which I've denoted QD with a bar over it. Or it can go to a positively charged electron muon or tau and its associated neutrino. On the left side, we have an antitop, which goes to a bottom antiquark and a quark-antiquark pair, or a negatively charged lepton and antineutrino. Okay, now that we know how tops are produced and how they decay, let's look at what CDF and D0 did. They looked at the process just described, but not quite all of the possible combinations of final states. Okay, so we saw that the W's decay into quark-antiquark pairs, or a charged lepton and a neutrino. But quarks, after they are produced, make jets of particles. These jets are more difficult to analyze than isolated leptons like electrons or muons, and are easily made in the detector by processes other than top production. And even among the leptons, we have the tau, which decays in the detector, making it less straightforward to deal with than electrons and muons. So, since quarks and taus are less straightforward to deal with, CDF and D0 designed their analyses to look for instances where at least one of the W's decayed to an electron or muon. In the case where both W's decay to an electron or muon, the top-antitop system leaves behind two jets from the B quark and antiquark, two charged leptons, and two neutrinos. The neutrinos do not interact with the detector, so are essentially invisible. So the signature to look for is two B jets, two charged leptons, and a transverse momentum imbalance from the invisible neutrinos. Alternatively, if one of the W's decays to a quark-antiquark pair, you get two B jets, two other jets, one charged lepton, and one invisible neutrino. So the signature, if the event could be ideally reconstructed, would be two B jets, two other jets, one charged lepton, and a transverse momentum imbalance from the invisible neutrino. Now, top decays almost always contain bottom quark jets. Jets from the other quarks, as well as jets from gluons, which also make jets, kinda look alike, making them hard to differentiate. But jets from B quarks can be partially distinguished from the like quark and gluon jets. So CDF and D0 used this information as well. Okay, so when particles collide and produce particles registered by the detector, that's called an event. There are lots of different processes that can happen inside a particle detector. The basic idea is to choose the events that look like the process you're interested in and discard those that don't. This is referred to as making selection cuts. You cut out the events that are probably not what you're looking for, and you keep the ones that are most likely to be what you are interested in. But you can't just check to see if you find the kind of events that you're looking for. You also need to make sure that the events you find aren't something else. This is because there are background processes that you're not interested in, but which can mimic the process you're interested in sufficiently well to pass your selection cuts. Let's look at some example backgrounds to top-antitop production. We could have a quark from a proton collide with an anti-quark from the antiproton and make a Z. That Z could decay to an E plus E minus or a mu plus mu minus pair. And if the quark and or antiquark radiates gluons, we can end up with a lepton pair and jets in the detector. This can start to look something like a top-antitop pair. Additionally, we could have production of a W pair or a single W plus some extra jets. And also, particles can be misidentified. We might look for a couple of isolated leptons in an event, but just how sure are we that the things we think are leptons actually are? These backgrounds need to be taken into account. So CDF and D0 had to estimate how many background events would sneak into their analyses. It's not enough to see events that look like top production. It also has to be that the number of top-like events you see is incompatible with the number expected from background processes. Okay, with that, let's look at the results that they got. Let's start with D0. With their selection cuts, they expected to see, on average, 3.8 plus or minus 0.6 events from background processes. They actually saw 17 events. From Poisson statistics, the probability of seeing 17 or more events when 3.8 plus or minus 0.6 were expected is about 2 times 10 to the minus 6. This is the p-value of their observed result. It quantifies how much the observed result disagrees with the expectation if the top quark didn't exist. The number is quite small, which means there is substantial disagreement. A p-value of 2 times 10 to the minus 6 corresponds to an excess of 4.6 sigma. Not quite 5 sigma, but close. CDF saw a total of 43 events pass their selection, 6 in the 2 lepton analyses and 37 in the single lepton analyses. In the 2 lepton analyses, where 6 were observed, 1.3 plus or minus 0.3 were expected from background. In the 1 lepton analyses, they looked at the number of jets identified as B jets instead of the number of selected events. And they used 2 different methods to identify these B jets. In the 37 single lepton events that they select, the 2 methods yield 27 observed B jets with 6.7 plus or minus 2.1 expected from background, and 23 observed with 15.4 plus or minus 2 expected. Some events had 2 identified B jets, and jets may be selected from both methods. When CDF combined all 3 types of analysis, they got a p-value of 10 to the minus 6. This corresponds to 4.8 sigma. Again, just shy of 5 sigma. So both experiments saw excesses slightly less than 5 sigma in their top searches. They simultaneously declared discovery and also gave initial measurements of the top mass. Let's briefly look back at the events they looked for in their single lepton analyses. On one side, you have a lepton, which helps identify the event as top pair production, but you also have a neutrino, which you can't measure. That makes measuring the mass of that top difficult. But on the other side of the event, you have a top quark that went to 3 jets. So in principle, you can measure the mass of that system. This is easier said than done, of course, in part because you have to make sure that you choose the right 3 jets to reconstruct the top quark. So this picture is a bit idealized compared to what CDF and D0 actually did. Okay. The 2 experiments each produced a measurement of the top mass. The error bars were large, but the values were compatible with the current measured value, which has an error bar of a fraction of a GeV. Lastly, I just want to point out that the top studies have continued ever since. While these initial studies were done using just a few dozen tops, the Tevatron went on to make about 300,000 of them. And the LHC has produced of order 1 billion tops. So this was just the beginning of the top story, and definitely not the end.